Hi everyone! Today we're doing lesson 5.4 where we're going to learn how to evaluate logarithms and graph logarithmic functions. So first what we want to do is we want to define a logarithm with base b. So if you let b and y be positive numbers with b not equal to 1, the logarithm of y with base b is denoted log base b of y here in the purple, and is defined as followed. Log base b of y equals x if and only if, so I can put these double-lined arrows, if and only if b raised to the x equals y. So it's important to see that a logarithm is simply defined by an exponential. So if I were to look at an example, for instance, 2 cubed, I know is equal to 8. Therefore, log base 2 of 8 is equal to 3. Notice how all of these pieces are working together. My base of my logarithm is the base of my exponential statement. So I can see 2 is the base of my exponential statement, and it is also the base of my logarithm. 2 is being raised to the third power. And so I can see how that power is translating in my logarithm. And then 2 cubed is equal to 8. So I can see here my y values and where they are sitting. A logarithm is telling you how much of, what percentage of a power you're using. They're inverse relationships of one another. We're going to explore that later on in the lesson too. And if you were in class and you did the what is a logarithm exploration with me the last class, then this all is really familiar to you. Let's take a look at another one. Let's say I have 7, oops, I don't want that one. Okay, I want 7 squared equals 49. So let's translate that into a logarithmic statement. So the base of my exponential is the same as my logarithm. So I have log base 7 of 49 is equal to 2 if I'm translating. Let's do one the other way. Let's start with a log. Log, let's say base 5 of 25 equals 2. And let's translate that. So when I'm translating from a log into an exponential form, let's carry my base over. So the base of my log is 5, so that'll be the base of my exponential. And it's going to be 5 squared is equal to 25. And I know that statement is true. So while I know that you guys are really familiar with all of these exponential statements, soon these logarithmic statements are going to come naturally as well. What I'd like you to do now is I would like you to pause the video and complete these exercises on your own, just translating logarithmic forms to exponential forms. So you'll see that either a logarithm or an exponential is given, and I just want you to translate it into the other form and then come back to the video when you are ready to check your answers. Okay, so let's see how you did. The first one, log base 2 of 8 equals 3, where our translation would be 2 cubed equals 8. The second one, log base 4 of 1 equals 0. You should have 4, oh goodness, sorry, let me erase that. We should have 4 raised to the 0 equals 1. Now we're going to move from exponential to log. I have 12 raised to the second power is equal to 144. So this translates log base 12 of 144 equals 2. The next one, 1/4 raised to the negative 1 equals 4. So I have log base 1/4 of 4 equals negative 1. The next one, we're going back the other way. I have log base 5 of 25 equals 2. So the translation is 5 squared equals 25. And then the last one, I have 3 raised to the negative 2 equals 1/9. So log base 3 of 1/9 equals negative 2. It is really important that you pay attention to your script when you're dealing with a logarithm. you remember you have log base b of y equals x. I may be switching up that x and that y, but it shouldn't really matter. Just make sure that you have your scripts down. So this b is going to be a subscript, and then everything else is in the same script. It's the same font. So now let's evaluate some logarithms. So I have a logarithmic expression, log base 4 of 64, and I want to know, what does that equal? Equals what? I'm going to put equals a question mark. So if I were to translate this into an exponential statement, you're saying 4 raised to what, I'm going to use a question mark, is equal to 64. Well, I know that 4 cubed is equal to 64. Therefore, log base 4 of 64 is equal to 3. So that would be how I evaluate that. So I can erase my question mark here if I wanted to and say it's equal to 3. Let's try the next one. I have log base 2 of 16. I don't know, it is equal to what? Instead of putting an x to a question mark, maybe let's just call it the variable x, because it's an unknown. So when I translate this, I'll have 2 raised to the x equals 16. Well, I know that 2 to the 4th power is equal to 16. Therefore, log base 2 of 16 is equal to 4. And you can erase this now if you want to as well. Say it equals 4. Let's take a look at the last one. I have log base 25 of 5 equals what? So we're going to set that equal to an unknown x, and let's translate it. You have 25 raised to what power equals 5? Well, if I were to take 25 raised to the first power, that would be 125, not 125. It would be 125. If I were to take 25 squared, I know that's going to be a lot larger when I take 25 times 25. Let's see what that is actually. 25 times 25 is 625. So I know that this exponent is not going to be 1 or larger. It's actually going to be a fraction potentially, or maybe even negative. So let's think of a relationship you know between 25 and 5. Well, I know that the square root of 25 is equal to 5. I know this. And I know that I could rewrite the square root of 25 as 25 raised to the 1/2. If I change this radical that I have right here into a rational exponent form. So that is where I'm going to be able to see that relationship, to see that log base 25 of 5 is equal to 1/2. So it's all about determining relationships and how the numbers are going to relate to one another. Next, what I want to do is I want to go over some 4 properties of logarithms. The first 2 we're going to be able to prove pretty easily. It says log base b of 1 equals, for right now, let's put it equal to an x. I don't know what that is. Well, let's translate that. You're saying b raised to what power equals a 1? And there's only one thing I could plug in for x that's going to make this true, and that's going to be a 0. And again, we're assuming here that b is a positive number, greater than 0, and we're also assuming that b is not equal to 1, because that was in my definition of a logarithm. So I know that b raised to 0 equals 1, and it doesn't matter what b is. So therefore, if I have log base b of 1, that will always be equal to 0. So for example, if I have log base 4 of 1, that would be equal to 0. Or if I have log base 14 of 1, that would also be equal to 0. If I have log base 18 of 1, that's equal to 0. Anytime you see a 1 here, it doesn't matter what that base is. It's going to be equal to 0. Now let's take a look at the next one. Log base b of b equals what? Let's set it equal to x and let's translate. Well, you're saying b raised to what power is equal to b? Well, there's only one thing that's going to make that true, and that's if b is raised to the first power. So if you have log base b of b, that will always be equal to 1. And let's look at some examples. If I were to have log base 20 of 20, it's going to be equal to 1. Or if I have log base 70 of 70 equals 1. Or log base 3 of 3 equals 1. All right, the next two are going to be a little harder to see, and I'm not going to be able to prove these just using the definition of a logarithm. When we get into lesson 5.5, we're going to revisit these, but for right now, you're going to have to trust me on these. So watch the script. This first one is b raised to the log base b of x. It will always be equal to x. And so what you do notice is hopefully that the base of the exponential, and then you're raising it to a logarithm, which has that same base. You should notice that those are the same, and based on our exploration, you have this inkling that this exponential and this logarithm, they feel like they're related in a special way, and we'll see that as we go through these lessons. But let's look at this as an example. If I were to have, for instance, 7 raised to log base 7 of 4, that would simplify to just be 4. Or if I had, 21 raised to the log base 21 of m, well, that would just be equal to m. Similar-wise, if I have log base b of b raised to the x, that is also just going to be equal to whatever x is here. For an example, if I have log base 6 of 6 raised to the 14th, that's going to be just 14. Or if I were to have log base 8 of 8 raised to the y, that'll just be equal to y. So here are my big properties that I have here so far. Apart from my definition of a log, here are 4 logarithmic properties that we should know moving forward. All right, so let's talk about a common logarithm versus a natural logarithm. You're going to want to pull out your calculator and take a look at these at your calculator while we're doing this. So a common logarithm is a logarithm with base 10. And it's in your calculator, and it is denoted LOG. It's what we've been working with, the LOG notation so far throughout this lesson. On your calculator, you should see an LOG somewhere on it, so you can take a look and see it. If you do me a favor and you just plug in or type that log, and then type 100, log of 100, and hit return, you'll see it says log of 100 is 2. And that's because anytime you don't see anything here, it is assumed to be a base 10. So if you type in log of 100, then you're saying 10 raised to what power equals 100, and it's 2. You could do another example for me, and you can put log of 0.1 or log of 1/10, and you'll see it returns a -1. And that's because 10 raised to the -1 equals 1/10. So that's a common logarithm, and it's programmed into your calculator because it is so common. Now the next one that's probably even more common is a natural logarithm. And a natural logarithm is a logarithm with base e. And we've talked about e a good bit. Remember, e is approximately 2.718 ... E is that number that shows up in nature anytime you're compounding something at a percentage rate, and it's continuously compounding, and it's always proportional to the amount that's present. It is going to grow at this rate of e, and it's just this phenomenon we see in nature. Also important and programmed in our calculators. So the big thing is with notation for e. So we're not ever really going to see anyone writing log base e of some number. We don't see that. It's so important that we actually gave it a new name. It's called ln. And ln stands for the natural logarithm, or logarithm of nature. And so that is why it's ln instead of nl. But yeah, anytime you see ln, that's just log base e. And so you should see that key in your calculator as well. As a matter of fact, if you type in ln of e, it's going to return, go ahead and type that in for me, and it should return a 1. And that's just because ln, right here, is really just log base e of e, and that's a property. We know that's just equal to 1, so you can see that there. So there's the difference between a common and natural log. Those are the only two logarithms that are programmed into your calculator. Now let's talk about their graphs. So if I'm graphing a logarithm with base b, let's think about some points that are like really easy that are always going to show up. So the first thing is, let's think about negative numbers. Do they exist? If I try and plug in a negative number, let's try and, we're just going to do it this way. Log base b of a negative number. What will that equal? Well, think about b raised to what equals a negative number. If I plug in positive exponents, well, they just get larger. And if I plug in negative exponents, they change into fractions. But does it ever actually equal a negative number? And the answer is it never happens. There's nothing I can do, there's no exponent I can plug in that would make this negative. What about 0? Does that happen? So if I take log base b of 0 equals what? Well, you're saying b raised to what power equals a 0. Well, we've already established that if I plug in positive numbers, I just get larger numbers, and if I plug in negative numbers, it just changes into a fractions. So it never is equal to a negative number. So right off the gate, I'm establishing that the domain is going to be all the numbers from 0 to infinity, not included. I'm not going to have anything on the left side of my y-axis happening. And then let's say, what's something easy to plug in? Something easy would be a 1 to plug in. I have a property there. If I plug in a 1, well, I have log base b of 1, and I know based on my property that equals 0. So I have the point 1, 0 on my graph. Another easy point to plug in would be b, because I've got log base b of b, and I have a property that says that's 1. So I have the point b, 1. I don't know where my base is. Let's just pretend it's right here. That would be my base. And then what does this graph look like? You know, from 0 to 1, what happens? Well, I know when I plug in fractional exponents that those numbers are going to get really, really, really large in the negative direction. So I know that as I get closer to 0, these numbers right here get really large in the negative direction. And then once I start at 1, those numbers will get larger. So it will grow. And here's what my graph kind of looks like. And obviously, you'll have some specific points. We have one example coming up. But this is what the basic formula looks like. My domain is from 0 to infinity. My range is going to be all real numbers. And let's see, and I will not hit y-axis, but I do have an x-intercept at 1, 0. So with all of that knowledge in mind, what do we think about f of x equals the natural log of x? Well, remember the natural log of x is just log base e of x. So think about the parent points I have. I know that 1, 0 will sit on the graph. I know that it's going to have this vertical asymptote situation going on. And I really should note that here too, that I've got a vertical asymptote because it's never going to hit that vertical line. And then my base is e, so I've got the point E1. So I'm going to about 2.71 and going up to a y value of 1. And that's, you know, that'll do. That's 2 points that kind of give me the curve. So if you were going to make a generalization about these, you know, we could draw kind of this shape. You know, you've got the point 1, 0. If the base of the log is here, then this would have to be 1. You got the point B1, and you know you have a vertical asymptote at x equals 0. And these are parent functions with no transformations. The domain is from 0 to infinity, and my range, of course, is all real numbers. Let's take a look at our last slide. And what we want to do is we want to look at the relationship between y equals 2 raised to the x and y equals log base 2 of x. So first what I want you to do is I want you to fill out these xy charts for 2 raised to the x and the log base 2 of x and see if you can determine any relationships. Okay, so when I wrote this before, I actually don't want to use these values. Sorry about that. What I want to do is use these values. My bad. Okay, so I'm going to keep going. You should too. I don't want to use that one. I'm going to use 2, 4, 8. Just to prove my point. Okay, so if you have not filled out your charts yet, you should pause the video and finish filling out these charts before we move on. But for everyone who's ready to go, let's take a look at this first point on both of these graphs. So what you have here on my exponential function is I have the point -3, 1/8. So -3, 1/8 is very small. It's about right here. And then what I have on my logarithmic graph is I have the point 1/8, -3 right here. So what you notice is that both of these points are not the reciprocals, the inverses of one another. The x value and the y value have flipped. Let's take a look at that next point right here, just from this group. So I have the first point from my exponential. I've got -2, 1/4. So it's getting a little bit bigger. I need the yellow one. A little bit bigger, going up to a 4th. And then I have 1/4, -2. So the x value is a little bit bigger. The y value is -2. So it should be going, it looks like mine are going to half, but I promise they're only going to a 4th. All right, let's look at the next point in my group. So for my exponential, I've got the point -1/2. And for my logarithmic, I have 1/2, -1. So I can see those points. They're getting smaller. It's getting ready to get interesting, I promise. All right, I think you understand what we're doing now. Let's go to the next one. On my exponential, I have the point 0, 1. On my logarithmic, I have got 1, 0. On my logarithmic, the next point, I have 1, 2. And for logarithmic, I've got 2, 1. For the next point on the exponential, I've got 2, 4. For the logarithmic, I've got 4, 2. And the last point, I've got 3, 8 on my exponential. For the logarithmic, I've got 8, 3. So at every step of the way, every point was an inverse of one another. And then I have my exponential function, which you studied in Algebra 1 and you've studied here in previous lessons. For my exponential function, I've got a domain of all real numbers. I've got a range that is 0 to infinity, because I know there's nothing I can plug into that x that'll make this exponential be 0 or negative. I have a y-intercept of 0, 1. On my exponential, not my exponential, on my logarithmic, you can see my two, in the last slide, I saw the points 1, 0, and then the base 1, so I can see those are my 2 parent points. But here with this chart, you can see many other points as well, so you can see that curve. You've got a domain that is 0 to infinity, a range that is all real numbers, and you have not a y-intercept, but an x-intercept of 1, 0. And you notice all of the points, x and y's, have been flipped. You also might notice that if I were to draw in the line y equals x, that if I were to flip the yellow line over the red line, I would land on the green line. And if you were to flip the green function over the red, I would land on the yellow. What this tells us is that these functions are inverse functions of one another. This is very important. I'm running out of space here, but I think I can sneak it in right down here. That f of x equals log base b of x, and g of x equals b raised to the x are inverses, meaning they undo one another. They have that special relationship that we've talked about. We know if we compose them, that you'll just get an x. They'll all compose back down to the function y equals x. And we're going to be able to use this relationship when we're solving logarithmic and exponential equations to get x's out of exponents or outside of logs. All right, the last thing I want to talk about is how do you evaluate logarithms using your calculator. Now, for those of you who have a newer TI-84, like a TI-84 Plus, you have a logarithm in your calculator. If you go to math and then you go to, I believe it's the fourth option, you can probably pull a logarithm and just type it in. But if you have an older calculator, you really need the change of base formula. And the change of base formula is really powerful in algebraic manipulation. It says that log base A of C is equal to log base B of C over log base B of A. And what you can do, what you're doing here is you are changing the base, and you can change it to anything you want. Most of the time, we change our base usually to a 10 or an E. Usually, that's just the most popular because they're already programmed in your calculator and you don't have to go into the math function. You can just see it right off the front panel. So it's important that you understand, though, that, for instance, if I want to evaluate log base 4 of 3, well, think about what I'm asked to evaluate here. It's equal to something, and I'm saying 4 raised to the what is equal to 3. Well, I know it's something, but it's not anything obvious. I know if I have 4 to the first power, that equals 4. If I do 4 to the negative first power, I get a 1/4. I'm way off. So it is likely some percentage. I know 4 to the 0 is equal to 1. So it's something in between 0 and 1 because 3 lies between 1 and 4. And it's going to be closer to 1 because 3 is closer to 4. But I'm just not quite sure what it is without a calculator. So what I can do is I can change the base. I can change it to a 10. If I change it to a 10, I've got log of 3 over log of 4. I can change it to an E, which would be ln of 3 over ln of 4. I mean, I can change it to anything I want, but I want to plug this in my calculator, so I'm going to use the ln option. I'm really a fan of natural logs. I think you should be too. Get used to natural logs. They're going to make your life pretty easy. And what I find is that log base 4 of 3 is equal to 0.792481. And what's interesting about that is if I take 4 raised to this 0.792481, I should get pretty darn close to a 3. There might be some rounding error. I encourage you to type this in with me. Oh, I got exactly a 3 in my calculator. So, not too shabby. All right, so at this point, you are all set to do problem set 5.4.